Hello everyone, welcome to another video of the course. In this video, we are going to solve the problem number 10 and so on, depending on how much time we have today. So let's start. Here is the problem 10. A single phase 10 kilovolt ampere 220 to 110 volt 60 Hz transformer is connected to a 220 volt supply. It draws rated current at zero point 0.8 power factor leading. The transformer may be considered ideal. A. Determine the kilovolt ampere rating of the load. B. Determine the impedance of the load. So, here the apparent power and rated voltage of the primary and secondary coils are given, and the primary coil is connected to a supply considering the rated voltage, right? The same rated voltage of the primary winding that we have. So here is the case. This is the ideal transformer. Okay. And the voltage of the primary, the rated voltage is 220. Excuse me. The secondary is 110. And we have a load here. This is ZL. And this is IL. The power factor of the load is also given, and here we have a voltage source Vs, the supply voltage, that is equal to 220 volt supply that we have here. So this is the supply, and the power factor of the load is 0.8. This is the voltage of the load VL, right? This voltage VL, because the power factor is leading, leading means that the load is capacitive. Yes. So the load current is ahead of its voltage. So this is the load current. How much is this angle? The phi angle. The phi angle is cosine inverse of 0.8. So how much is that? This is the cosine inverse of 0.8. We should multiply it by 180 divided by pi to calculate in degrees. So 36.8. The phi angle is 36.8. So this is the parameters, the inputs of this problem. Yes. So how we can determine the kilovolt ampere rating of the load? Because the transformer is ideal, so we don't have any loss in it, is lossless. So the power of the supply, right? The total power of the supply will be transferred to the load. Here, this is equal to the rated voltage of the primary coil. So the apparent power of the transformer is equal to the apparent power of the load. What is the apparent power of the transformer? Is 10 kilovolt ampere. Okay, this number here, that is equal to the apparent power of the primary, that is equal to the apparent power of the secondary, right? Equal to VP/IP Vs/Is. How much is the value of the primary coil current? The current of the primary winding is SP divided by VP. SP is 10 kilovolt ampere, right? 10 times 10 to the power 3 to have it in volt ampere divided by 220. That is 45.45 amps. We can calculate the current of the secondary winding using a similar equation, but also if we know the turns ratio, we can calculate it using this equation. What is the turns ratio? Is the ratio of the primary voltage, right, per secondary voltage. That is equal to 220 divided by 110. That is equal to 2, right? The turns ratio. N1 divided by N2, right? This is N1, the number of turns in the primary coil. N2 is the number of turns in the secondary coil. So the turns ratio is defined as this fraction. So the current of the secondary coil is equal to 2 times I primary, that is equal to 90.91. So we have the current of the load actually, right? The current of the secondary is the same as the load current, and we have the load voltage, so we can calculate the load impedance, that is equal to Vs divided by Is. The value of the Vs is equal to 110 and the value of the Is is 90.91. That is equal to 1.21 ohm. This is the amplitude of the impedance, right? So what is the value of the impedance, resistance, and reactance? Actually, the components of the impedance, we can use these two equations, right? We know the power factor, so we calculated the phi. Then we can calculate the resistance and reactance of the load. So you know that. Here is the complex plane. This is ZL. We have this phi angle. So the real component is the resistance and the imaginary component is the reactance of the load, right? So the resistance is ZL times cosine of phi, and reactance is ZL times negative of sine of phi. I used these equations here and calculated the resistance and reactance of the load. The value of the resistance is 0.96 and the value of the reactance is negative 0.72 ohm. So yes, this is the procedure for solving this problem, and you should consider this point. The voltage of the supply is the same as the rated voltage of the primary. The load current is rated one, so this current, the rated current of the secondary, and the power factor is leading. Leading means capacitive, lagging means inductive. So you know that. Anyway, let's go for the next problem. Problem 11. Okay. For a circuit shown in this figure, figure P2.11, consider the transformer to be ideal with the turns ratio 1 to 100. So here we have the turns ratio. The transformer is ideal. Calculate the actual load voltage V2 and the supply current I1. So here is the circuit, of the problem 11. We should calculate V2, the voltage of this resistance, and also the I1, the current of the supply. Okay, so how we can solve this circuit? We can transfer the components, right? These elements from the secondary side to the primary. So we will have this circuit, and simply we can solve this circuit, calculate components, and then transfer the value of the V2 again to the secondary to calculate the actual value of the V2. Yes. How we can transfer the impedance, right? Here we had the case for the problem 9 that we referred the load impedance from the secondary to the primary. This was the equation. So here, again, let me copy this. This is the circuit of the problem. How we can transfer these two components to the primary in this direction, right? First, you should look at the number of turns of this side, that is 1, then 100. So minus J, 20 kilo ohm, that is 20,000 ohm, times 1 divided by 100 to the power 2, that is equal to negative J2. Yes. How we can transfer this resistance? Using the same equation. So this is 30 kilo ohm, or 30,000 times 1 divided by 100 to the power 2, that is equal to 3. This is the circuit. In this case, we have this voltage source, the I1, right? The current of the voltage source. This is the reactance here. This is in the primary side, right? Without change, we have it here. And here are two transferred elements, right? Referred from the secondary to the primary. Negative J2 ohm, and this is 3 ohm. So in this case, V2 becomes V2 prime. Yes, this is the value of the resistance voltage, the voltage of this resistor referred to the primary. When we do the calculations, again, we should transfer it to the secondary side. So for this circuit, what is the total impedance? We have these three components in series, right? These three elements, this inductor, this capacitor, and this resistance. So we have this summation J5 plus 3 minus J2, that is 3 plus 3J. This complex number. How much is the value of the current? I1 is equal to 20 divided by Z total. That is equal to 3 plus J3. So in this equation, we considered the angle of this voltage source equal to 0, right? Reference angle. We need to consider the angle of one voltage or one current source as reference to do calculations. So in this case, this is actually this one, 20. This is the RMS value and its angle is 0. Okay, as reference in our calculations. So here is the value of the current. The amplitude of the current is 4.71. Its angle is negative 45 degrees. Okay, and how we can calculate the V2? We can transfer the value of the current to the secondary side first. So I2 is equal to I1 times 1 divided by 100. Okay, that is equal to this one. And finally, we can calculate V2, that is I2 times the value of this resistance that we have here, 30 kilo ohm. So because I transferred the current to the secondary side, we should use the actual value of the resistance, not the referred value, right? This is important. Otherwise, you calculate this V2 wrong. And this is the value of the V2 in this case. So let's solve this problem using the ANSYS Simplorer and check out our calculations, the amplitudes and angles. So here simply we can add a new Simplorer design for problem 11. From basic elements we can add a transformer, ideal transformer. So the turns ratio is 100. This is N2 divided by N1. Okay, here you can see the turns ratio, that is 100. And now let's add these components. We have one inductor here. What is the value of the inductance of this inductor? Let's consider 60 hertz, right, for our calculations. Here the frequency is not given. I am going to consider it equal to 60 hertz. So this is equal to 5 ohm divided by 2 times pi times 60. Yes, you know that for an inductor we have this. The reactance is equal to omega L. So inductance will be equal to the reactance divided by omega, or reactance divided by 2 times pi times F. Here we should specify inductance. And we have a voltage source here. This is sine, right? Sinusoidally excited. The amplitude is 20. The magnitude and the angle let's consider it 0, the reference angle. So, okay. And we have this capacitance, right? This capacitor here. So let's set the value of the capacitance. You know that for a capacitance, we have this. The value of the reactance is equal to 1 divided by omega C. So the value of the C will be equal to 1 divided by x omega. Yes. So in this case, we have this is equal to, we need to transfer it to the primary or not? No, because here we consider this transformer and we should use the actual values. So this is 20,000 divided by, excuse me, 1 divided by 20,000 times 2 times pi times 60. That is omega. Okay. Finally, we have this resistor here. What is the value of the resistance? Is equal to 30 kilo ohm or 30,000. Oh, yes, that's all. Now we can run this analysis to calculate the current of this source and the voltage of the R1. So again, let's add this AC solver 50 and 60. I'm going to solve only for these two frequencies. We can analyze the circuit to check the components. Also, you can add ground for reference in the primary and secondary side. So from results, let's check the value of the current E1.I, the current of the voltage source. Here we have this one, and the voltage of the R1. So let's show it in the magnitude and angle. Also this one. Okay. How much is the value of the current of the source, the amplitude? 4.71. This number. Okay. And the value of the voltage V2 is 1.41 kilovolt. Okay. So we have the same value here, 1.41 kilovolt. Also check the angles, right? Negative 45, negative 45. So yes, using this transformation, we can simply solve this circuit and then transfer components again from the primary to the secondary and calculate actual values. So you can repeat this problem. Also use the ANSYS to validate your calculations. Anyway, okay, so let's go for the next problem. Problem 12. A single phase 2400 to 240 volt transformer has R1 equal to 0.75 ohm and X1 equal to 1.5 ohm. It is drawing 100 amps at a lagging power factor of 0.8 determine the induced voltage E1 in the primary winding. So in this problem, the value of the resistance and the leakage reactance of the primary winding are given. The value of the rated voltage of the primary is known, and we have this current and the value of the power factor. We should calculate the value of the E1. But in this problem, we don't know that this current is for the primary winding or for the secondary. Because of this, we can propose two cases. In the case 1, we assume that this current is for the primary winding, and in the second case we assume that this current is for the secondary. So we can solve these two cases. Okay, so here we can see the case 1. In this case, we have this voltage for the V1, and this is the amplitude of the current, 100 amps. This is the angle of the current phasor with respect to the V1, because the power factor is zero 0.8. So you know the angle, when the value of the power factor is 0.8, we can write, yes, this to find the angle. This is the angle between the current and the voltage. So here we have also the value of the current for the secondary winding. We know this transformation and we can calculate this current. In this case, the case 1, just we can write a KVL for this loop for the primary side and calculate E1, right? Not too complex. So here is the case 1. The value of the I1 is 100 amps. This is the angle. This is in the real and imaginary format. What is the value of the voltage drop on this resistance? And this reactance is the current times the impedance of the primary winding, that is equal to this one. In this equivalent circuit of the transformer, the magnetizing branch is neglected. We don't have a magnetizing branch here. So the value of the E1 will be equal to the V1 minus the voltage drop. That is equal to this one. The amplitude of the E1 is 2251, and its angle is negative 1.9 degrees. Here is the vector diagram. In this case, you can see the I1 phasor, the E1, V1, and this is the voltage drop. Here in MATLAB, we have this code for the problem 12, case 1. You can use this M file to generate the vector diagram. So here is the value of the I1, the current of the primary winding, the amplitude times the E to the power. This is the imaginary unit times the angle, the phase of the I1. This is the impedance of the primary winding, and this is the voltage of the primary. Why the voltage of the primary is just a number? Because its angle is 0, right? This is on the real axis. So this is the value of the voltage drop. And finally, this is the value of the E1. Let me copy this code. Just I want to show the amplitude of the E1 at the end of this M file. Here I generate the phasors and add them to the axis. As you know, we need to set the scales properly because the amplitude of the voltage is different from the amplitude of the current. We need to set scales to generate a good phasor diagram. Also here I used this function add vector to plot the voltage drop vector. In this case, you need to specify the start point and the end point of the vector. So if I run this M file, here you can see the amplitude of the E1. Yes, we calculated the amplitude of the E1 here. And this is the phasor diagram. You can select this option to pick up the tags and adjust the location of the tags. This is the I1, this is the V1, the black vector, this is E1, and this is the voltage drop. We know that E1 plus the voltage drop is V1. So, yes, this is the procedure for solving the case 1. But what about the case 2? In this case, we assume that this current is for the secondary winding, this one. So, what will be the angle of the V1 phasor? We don't know. Yes. In this case, this is V2. This is the voltage of the load impedance. And we know the angle of the I2 with respect to V2. We can consider that the power factor is for this current and voltage combination for the load. Okay. So in this case, we can calculate the I1 using the transformer turns ratio. Yes, here is 100. The ratio is 10 to 1. So the value of the current for the primary will be equal to 10. And if we neglect the voltage drop for these elements, these two, we don't have any information. We can assume that the angle of the E1 is also 0. Yes. So in this case, we know the amplitude of the V1. We know the angle of the E1. We know the current. And we are going to calculate the amplitude of the E1 and the angle of the V1. Yes, a little bit more complex than the previous case. How we can solve this problem? Because the angle of the E1 is 0, we can consider this vector diagram. This is the case. We have V1, we have this resistance, this reactance, and this is E1. This is the current, I1. So you know that this is the XY plane, the complex plane. This is the real axis and this is the imaginary. So this is the E1, okay, E1, and this is the value of the current, I1. Let me plot an exaggerated value for the voltage drop. The voltage drop is equal to Z1, the impedance of the primary winding, times I1. So this is the voltage drop, VD. Okay, the voltage drop. And what is the value of the V1? V1 is this phasor. Okay, so this is the phasor diagram in this case. We know this angle, right? The power factor is 0.8. And what is the relationship between the amplitude of the V1 and these two phasors? We can decompose this vector into its components, the real component and the imaginary one. So we have a triangle here. Yes, you know that V1, its amplitude to the power 2 is equal to E1. This is a real number plus the real part of the voltage drop to the power 2 plus the imaginary part of the voltage drop to the power 2. So we know this value, so we can calculate E1. Finally, when we calculate E1, we can calculate this angle, the angle of the V1 phasor. Yes. So here I implemented this equation. This is the value of the current in the primary, that is equal to I2 divided by 10. This is the value of the voltage drop, and we know that the amplitude of the E1 is equal to this expression. If you replace the numbers, finally we will have this amplitude for E1. Here you can see this phasor diagram. So, as you can see, the amount of the voltage drop is very low. Yes. Here, this is the M file for the case 2. The value of the I1 again, Z1, V1 amplitude. Yes. This is the value of the voltage drop, the amplitude of the E1, and this is the V1 phasor. After calculation of the E1, we can calculate V1. So if I run this M file, here you can see the voltage drop. However, it is very small here, the length of the voltage drop. So what is the value of the E1 is equal to 2384, 85, close to this number, 85. So yes, this is the procedure for calculation of the amplitude of the E1 in the case 2. However, as you can see, the value of E1, the angle of the V1, let's multiply it by 180 divided by pi, is 0.17 degrees. Very low, right? Even you can consider the value of the angle of the V1 equal to 0, recalculate and compare the value of the E1. Its amplitude is important. Okay. So yes, this is the exact case, but also you can neglect the angle between E1 and V1 because the voltage drop is not too high, as this is practical, right, for transformers. We shouldn't have a high voltage drop on the primary resistance and the leakage reactance. Otherwise, the efficiency of the transformer will be low. Anyway, you can review this problem and redo these calculations yourself. So let's go for the next problem, problem 13. A single phase 100 kilovolt ampere 1000 to 100 volt transformer gave the following test results. Results for the open circuit test and the short circuit test. We have this information. A. Determine the rated voltage and rated current for the high voltage and low voltage sides. Okay. The value of the rated voltage for the both sides are given here. This is the rated voltage of the high voltage side, and this is the rated voltage of the low voltage side. Also, the apparent power of the transformer is given 100 kVA. We can calculate the current of the high voltage side and the current of the low voltage side. This is the case. Let me draw these two coils here. This is the high voltage side and this is the low voltage, 1000 volt, and here the value of the voltage is 100. What is the value of the current for the high voltage side? Is the apparent power divided by the voltage. So 100,000 divided by 1000 is equal to 100 amps. Yes, this is the current of the high voltage side. What is the value of the current of the low voltage side? The turns ratio is 10 to 1. So this should be equal to 1000 amps, right? So here we have the current of the low voltage side, 100,000 divided by 100, that is equal to 1000 amps. Okay. Part B, derive an approximate equivalent circuit referred to the high voltage side. So how we can calculate the equivalent circuit for the high voltage side? Data for two tests are given. We can use the open circuit test data to calculate the parameters of the excitation branch and the short circuit data to calculate the equivalent resistance of the primary and secondary windings and also the leakage reactance. Yes. So the open circuit test is the first one. In this case, we have this configuration. This is the high voltage side and low voltage. We have 1000 volt, 100 volt here. As described here in the open circuit test, the high voltage side is open and we connect the source voltage or the open circuit voltage to the low side. Here you can see the value of the open circuit voltage is 100. That is equal to the rated voltage of the secondary side. Yes, the value of the current is 6 and the power loss in the open circuit test is 400. This is for the core loss. Okay, so here we connect the voltage source here, V open circuit, the value of the current, I open circuit, is equal to 6 amps. The value of the voltage for the open circuit test is 100, equal to the rated one here. The aim is to calculate the RC and XM for the magnetizing, right, of the transformer. So this is RC. It is better to write RC calculated for low voltage side. Okay, and similarly this is XM for low voltage side. The high voltage side is open, so we should consider this because the aim is to calculate the equivalent circuit parameters referred to the high voltage side. So what is the value of the equivalent core resistance? We can calculate it using this equation. We did it before, right? This is the circuit for the open circuit test, and we solved a similar problem here, problem 4. This is the vector diagram, and these are equations used to calculate RC and the magnetizing inductance. So just let's use them here. The equivalent core resistance at the low voltage side is the open circuit voltage to the power 2 divided by the power loss, that is equal to 400. This is the value of the voltage, 100. Finally, the value of the resistance is calculated equal to 25 ohm. What is the value of the equivalent core resistance? Current is the power of the open circuit test divided by the voltage of the open circuit, that is equal to 4 amps. Okay, and how we can calculate the amplitude of the magnetizing current is equal to the current of the open circuit test, this current, that is equal to 6 amps, minus the equivalent core resistance current to the power 2, that is equal to this one, 4.47 amps. Knowing the value of the IM, we can calculate the magnetizing reactance, that is equal to the voltage of the open circuit divided by the magnetizing current, that is equal to 22.3 ohm. So how we can calculate the referred quantities to the high voltage side? Okay, how we can calculate and refer these quantities? This is the turns ratio, 10 by 1. First, we should look at this number and then this number. So XM referred to the high voltage side is XM low voltage times 10 divided by 1 to the power 2, that is 100. So here we can multiply the equivalent core resistance and the magnetizing inductance by 100 to calculate the corresponding values referred to the high voltage side. So what is the next test? Is the short circuit test. And here is the case. As you know, in the short circuit test, we neglect the excitation branch, and the aim is to calculate the equivalent resistances of the primary and secondary winding, and also the leakage reactance. So here we have the value of the voltage and the current. What is the value of the impedance? Is equal to V short circuit divided by the I short circuit. That is equal to 50 volt divided by 100 amps is equal to zero point 0.5. Yes, here is the case. In the short circuit test, we have this configuration. This is the high voltage side, and this is the low voltage side. This is 1000, 100. We have this turns ratio. We connect the voltage source here. This is the voltage of the short circuit. The aim is to calculate the equivalent resistance and the leakage reactance. This is R equivalent, and this is X equivalent, JX. So yes, this is Z equivalent, the internal impedance of the transformer. We know the value of the current, I short circuit, and we know the power loss. Okay, so here is the value of the impedance. Why I wrote here high voltage? Yes, because we do this test on high voltage side. As you can see, the value of the current is 100 amps here. Yes, in the short circuit test, we increase the voltage gradually and short circuit the secondary side. We increase the voltage until getting the rated current here. What is the rated current here? Is 1000 amps. And when we have 1000 amps here, the current of the primary will be 100. Yes. So this is the current of the short circuit, similar to this one, voltage of the open circuit. So the value of the Z equivalent for the high voltage side is 50 divided by 100, that is 0.5. What is the value of the equivalent resistance? Is the power loss in the short circuit test divided by the current of the short circuit to the power 2. If you replace the numbers, the power loss in the short circuit test is 1800 watts divided by the current of the short circuit to the power 2. That is equal to 0.18 ohm. And finally, we can calculate the equivalent leakage reactance. That is SQRT of Z equivalent to the power 2 minus R equivalent to the power 2. That is equal to 0.466. So we calculated parameters of the equivalent circuit referred to the high voltage side, and now we can draw this equivalent circuit. Here you can see the value of the parameters, right? The equivalent core resistance, the magnetizing reactance, equivalent resistance of the primary and secondary windings, and the equivalent leakage reactance. So let's go for the part C. Determine The voltage regulation at full load, zero point 0.6 power factor leading. So, before answering this part of the problem, let's review the definition of the voltage regulation. Okay, what is the definition of the voltage regulation and why it is important? So let's check the reference. Here we have this section 2.3 voltage regulation. Most loads connected to the secondary of a transformer are designed to operate at essentially a constant voltage. However, as you know, as the current is drawn through the transformer, the load terminal voltage changes because of the voltage drop in the internal impedance of the transformer. Yes, like this one that we calculated in the previous problem. We calculated the value of the voltage drop. So this is the voltage drop is because of the series impedance. Yes, here is the equivalent circuit of the transformer. And when we connect the load to the secondary side, we have a change in the value of the voltage. This is the corresponding vector diagram that we discussed this vector diagram in the previous problem. Okay, this is the Z equivalent. This is the value of the load voltage, and this is the value of the primary voltage. So when the load is not applied to the transformer, the open circuit case, the total terminal voltage is this one. Yes, the value of the voltage for the secondary side is V1 divided by the turns ratio. Yes, this is the voltage of the secondary at no load. But when we switch the load and close the switch, connect the load to the secondary, this will be the value of the voltage when we have load, right? V2 when we have load is equal to the value of the V2 for the no load case plus or minus delta V2. The plus or minus sign depends on the nature of the load, whether it is inductive or capacitive. This voltage change is due to the voltage drop in the internal impedance of the transformer. So a large voltage change is undesirable for many loads. Yes, the aim is to have a constant voltage amplitude for the secondary side of a transformer. So how to define a parameter to measure the variation in the amplitude of the secondary voltage? A figure of merit called voltage regulation is used to identify this characteristic of the voltage change in the transformer with loading. The voltage regulation is defined as follows. The amplitude of the V2 for the no load condition minus amplitude of the V2 for the loaded case divided by the amplitude of the V2, right? For the loaded case when we have a load at the secondary. Sometimes in other references, maybe, right, they have a slightly different definition. They use this term in the denominator of this fraction. Anyway, but results are close. Okay. So the absolute signs are used to indicate that the change is magnitude is important, right? not phase. The change in the amplitude of the secondary voltage is important. So we use the amplitudes here. We can calculate voltage regulation using other equations. Also, if we transfer these quantities to the primary side. So if we translate these quantities to the primary, we can write this equation. Yes, V2 prime at no load minus V2 prime, right? When we have load, just we transferred all of the quantities in this equation to the primary side. And the load voltage is normally taken as the rated voltage. So I will calculate the voltage regulation and explain this part. So here you can see the summary of these equations in this slide. Okay, the voltage regulation, the corresponding definition when we have quantities at the primary side. How we can calculate the voltage regulation for our case? In our case, when we don't have any load, when the current of the secondary side is 0, the V2 prime at no load condition is equal to 1000. The angle is 0. Yes, we don't have any current here. We don't have any current here. So the voltage here for the V1 is equal to this one, V2 prime at no load. And when we have full load condition, the value of I1 will be equal to I2 prime, or actually I2 divided by 10, that is equal to this one. Why? Because the power factor is 0.6 leading. The load is capacitive. Yes. Here we have this. The power factor is 0.6. Excuse me. The value of the phi is 53.1. This angle. This is the value of the current. How much is the value of the voltage drop? Is equal to this one, the current times this branch, the impedance of this branch. And finally, here, because we consider the power factor, the angle between the current of the secondary and voltage of the secondary, we consider the angle of the V2 prime for the full load case equal to 0, similar to this case 2 that we solved. Yes, we assume the angle of the V2 prime at full load equal to 0, and we calculate its amplitude using this equation. We know the value of the voltage, yes, the high voltage V1, and we have these two numbers, the imaginary part of the voltage drop and the real part. So if you replace the numbers, this will be the value of the V2 prime for the full load case. The load is capacitive and the value of the voltage here is higher than the value of the V high voltage. Yes. So if you replace the numbers in this equation, the value of the voltage regulation is equal to minus 2.5%. So if we express this in percentage. So here is the M file for the problem 13. So let's review the code to calculate the voltage regulation and compare with the number that we have here. So we have these inputs. This is the rated apparent power, okay, the kilovolt ampere. So this is the apparent power. This is the voltage of the high voltage side, the low voltage side, open circuit voltage, the power loss in the open circuit test, the current of the open circuit, the short circuit voltage, the power of the short circuit test, and this is the current of the short circuit test. Here we have these outputs. Yes, I implemented these equations here. Equations of this slide. And if I run this M file, you can see these numbers. For example, the equivalent resistance core current, the magnetizing current, and so on. You can check the value of the parameters that we have here with these parameters that we calculated anyway. So let's calculate the voltage regulation. Here is the part for calculation of the voltage regulation. The value of the voltage V2 for the no load case is 1000 volt. This is V2 prime for the no load. And when we have this current in the secondary, the value of the I2 prime in the primary is this one. Yes. Here is the voltage drop that I calculated it here. This is the value of the current I1 full load 100 amps times this one. The power factor is leading. The load is capacitive. So this is the value of the voltage drop, and this is the value of the V2 for full load condition. This one, I implemented this equation we discussed, and this is the value of V1 for the full load case. And finally, this is the value of the voltage regulation, V2 prime at no load. This equation, yes, and V2 prime for the full load. This is the amplitude. Also, this is the V2 prime full load. So if I run this code, the value of the voltage regulation is minus 2.5. This is the vector diagram. Here you can see the value of the I1 for the full load case. This is V2 prime for the full load. This is V1 for the full load, and this is the value of the voltage drop. Yes. So in this case, the load is capacitive. You can compare this vector diagram by this one. Here, the load is inductive. So in this reference also, we have this equation for calculation of the voltage regulation. In this case, we consider the value, the amplitude of the V1 constant for both cases, and we calculate the change in the value of the secondary voltage, right? The amplitude of the V1 full load, let's check here. Amplitude of the V1 for the full load is the same as the amplitude of the V1 for the no load. Just we calculate the change in the amplitude of the V2. Yes, to calculate the voltage regulation, how much drop or increase we have in the value of the V2. V2 full load here is higher than 1000. Yes, because the load is capacitive. Yes, but we can do a reverse calculation. Yes, we can consider the amplitude of the V2 constant, and for the full load case, we can calculate the value of the V1. We can consider V2 prime equal to the rated one, and for the no load case, okay, this is equal to the V1. For the full load, we will check how much increase we will have in the value of the V1. Yes, the calculation is even more simple. Yes, is similar to the case one. Okay, here, if we consider the V2 rated, let me copy this code here. This is the current of the full load I1. If I copy this, the value of the V2, let's change the name for the rated. I consider it equal to 1000. This is the value of the voltage drop. And what is the value of the V2 for full load? Again, we can consider it equal to the rated one. And in this case, I am going to calculate the rise in the value of the V1 voltage. That is equal to the V2 rated plus the voltage drop. So this is V2 rated, and this is the absolute value of the V1. Yes, this equation. So a counterpart calculation. Yes, here in this case, we assume a fixed number for the amplitude of the V1 and calculate the variation in the amplitude of the V2. And in this case, let's write the voltage regulation using the new method. We fix the value of the V2 and calculate the rise in the amplitude of the V1. So if I run the code, here as you can see, for the previous case, the voltage regulation is negative 2.5, and for this new case is negative 2.55 kilos, right? So if I even increase the value of the current, for example, 200, again, you can compare the values for the voltage regulation, right? These are kilos. You can also use this method. This method doesn't need this calculation. Yes, just we sum up these two terms. And if you look at the last example of this chapter, this method is used for calculation of the voltage regulation. The system in this example is per unit. We will discuss the per unit system in the next problem. So here the value of the V2 is set equal to 1 per unit, and we calculate the amount of the rise in the amplitude of the V1 and calculate the voltage regulation, the second method that we used in this M file. Anyway, so you can use this M file, run the code, generate the vector diagram for different operating condition, and calculate quantities, compare. Okay, so the last point of this video is the maximum voltage regulation. As you can see here in this figure, when we change the value of the power factor, the load power factor, theta 2, the V1 phasor moves on this circle. Okay, so for a fixed load current amplitude and a varying power factor, when we have maximum voltage regulation, the maximum voltage regulation occurs when we have maximum amplitude in V1. Yes. And according to this figure, when we have a maximum value for V1, let me copy this here. This is the theta 2, depends on the power factor. This angle is theta 2 plus theta equivalent 1, the angle of the internal impedance of the transformer. The maximum value of the V1, maximum amplitude of the V1 occurs when V1 is on x-axis, is here. Okay, so let me use another color, this one. This is the value of the V1. Yes, this case. When the V1 phasor is on x-axis, we have maximum difference in amplitude of the V1 and V2 prime. So this results in the maximum voltage regulation. The maximum voltage regulation is when this summation is equal to 0. Yes. So here is the condition. You can check this condition here. The maximum voltage regulation occurs if the power factor angle of the load is the same as the transformer equivalent impedance angle and the load power factor is lagging, right? So this is important, and this is the condition for getting the maximum voltage regulation. We have a problem later to calculate the maximum voltage regulation, and you should remember this condition according to this phasor diagram. Anyway, I think this is enough for this video, and let's continue solving the next problems in the next video. Thanks for watching.